All right, in this explainer, we're going to pull back the curtain on one of the most fundamental ideas in all of programming, how software actually makes choices.
I mean, really, have you ever stopped to think about it? How does your phone know to silence a call when you hit the volume button? Or how does a video game know you finally leveled up? It all comes down to the code making millions of tiny little decisions.
And here's the secret. It's not magic, not at all. It's actually just a series of incredibly simple yes or no questions asked at lightning speed. But that brings us to the core problem we're going to solve together today. What happens when a program gets something it doesn't expect? Just plain bad data?
Okay, let's dive right in with our first section, a problem of bad input. This is really where the whole story begins.
So imagine you've written a simple program to calculate the area of a circle. You pop in the radius, it does the math, and boom, you get an answer. It works perfectly, right up until someone types in a negative number for the radius. Mathematically, that's just nonsense, but the program doesn't know any better. It'll just spit out a garbage result. So the question is, how do we stop this from ever happening?
And that brings us to our very first, and maybe most important, tool for making decisions in code, the simple but oh so powerful if statement.
But before we can even use an if statement, we have to understand the language of computer decisions. And that language is called Boolean. A Boolean value is the simplest thing you can imagine. It can only ever be true or false. That's it. There is no maybe. It is the computer's ultimate version of yes or no.
So how do we get one of those true or false answers? Well, we use these things called comparison operators. They let us ask really basic questions like, is this number less than that one? Or are these two things exactly equal? The answer to any of these questions is always, without fail, a Boolean value, either true or false.
And this is where the if statement finally comes in. I like to think of it as a one-way gate. First, you ask a true or false question. If the answer comes back true, the gate swings open and a specific chunk of code gets to run. But if the answer is false, the gate stays shut. The program just skips that code and moves right along.
So let's go back to our circle problem. We can now write if the radius is greater than or equal to 0, then go ahead and calculate the area. And hey, it works. It totally prevents the bad calculation. But what happens if the user does enter a negative number? Well, the program just stops. It does nothing. It just ends without any explanation. Not exactly helpful, right?
Now, before we fix that, I have to show you this tiny but absolutely devastating mistake that beginners often make. See that single semicolon after the question on the left? That little dot basically tells the program, okay, the if statement is over now, thanks. So the code inside the curly braces, the code that's supposed to be protected, it will always run, no matter what. It's a classic bug that is an absolute nightmare to track down.
So yeah, just having the program stop when the input is bad isn't going to cut it. We need a way to choose between two different actions. And this brings us to the next level of decision-making, the if-else structure.
The if-else statement is pretty much what it sounds like. It's a true fork in the road for your code. If the condition is true, the program goes down one path. Else, which just means in every other situation, it goes down the other path. Every possibility is handled. No more just doing nothing.
And this gets us to our complete, elegant solution for the circle problem. Now we can say, if the radius is okay, calculate and print the area. Else, print a helpful error message like negative input is not allowed. And just like that, our program is robust. It can handle both good and bad data with no problem at all.
But what if you have more than just two choices? Think about assigning letter grades. It's not just pass or fail. You've got A, B, C, D, and F. For this, we can chain our statements together into what I call a multipath road using else if. The program checks the first if. Is the score 90 or above? Nope. Okay, else if it's 80 or above? Nope. It just keeps going down the line until it finds a condition that's true.
So checking one thing at a time is great, but the real power comes when we start crafting smarter, more complex questions. And we do this by combining our simple checks using what are called logical operators. There are really just three main ones you need to know. First, there's not, that exclamation mark. It just flips a Boolean value. True becomes false, false becomes true. Simple. Then there's and, the double ampersand. It's very strict. It only gives you a true if the conditions on both sides of it are true. And finally, we've got or, the two vertical bars. It's much more relaxed. It'll give you a true if at least one of the conditions is true.
All right, let's put these new tools to the test with a classic brain teaser. How does a program know if a year is a leap year?
The rule is surprisingly tricky. A year is a leap year if it's divisible by 4, unless it's also divisible by 100, except for the years that are divisible by 400. So how in the world do you write that as a logical question? Well, with our logical operators, you get this, a single, beautiful line of code that perfectly captures that complex logic. That little percent sign, by the way, is the modulo operator. It just gives you the remainder after a division. So this line is really asking, is the year divisible by 4 and not divisible by 100? Or, as a completely separate check, is the year divisible by 400? Pretty cool, right? That is the power of asking smart questions.
Now, as powerful as they are, those long if-else chains we saw with the letter grades, they can get a little messy, a little hard to read. So for certain situations, there's a much cleaner alternative.
And it all comes down to clarity. Check out this example for finding a tax filing status. On the left, you've got that clunky if-else-if chain. I mean, it works, but look at the switch statement on the right. It's so much easier to read. It just says, okay, let's switch based on the status variable. In case it's 0, do this. In case it's 1, do that. It reads just like a table of contents for your code's choices.
Now, there are a few key rules for a switch. It's best when you're checking one variable against a list of specific values. And that break keyword you see, it is absolutely critical. If you forget it, the code will run a case and then just fall through and run the code for the next case too, which is almost never what you want.
And finally, here's a little pro tip you'll see all the time in professional code. It's called the conditional or ternary operator. It's just a super compact way to write a simple if-else statement on a single line. You ask a question and then provide one value if it's true and a different one if it's false. It's not something you have to use, but it's very concise.
So let's do a quick recap of our decision-making toolkit. We've got the if statement. That's our one-way gate. Then the if-else, our two-way fork in the road. We have else if for building that multi-path road with lots of options. We have the logical operators, the brain that connects all our questions. And finally, the switch statement, which is like a clean, multi-door hallway for specific choices.
So I'll leave you with this final thought. The next time your music app suggests the absolute perfect song for the moment, or your GPS instantly reroutes you around a sudden traffic jam, just take a second. Can you picture it? Can you see the thousands, maybe millions of these simple if-else decisions firing off in milliseconds, all to make that little piece of magic happen?